Our group chose to design and manufacture a prototype of an air intake system for a Formula SAE car. The air intake of a Formula SAE car consists of an air filter, a throttle body, a venturi tube, a plenum, 4 runners, and a base plate. The air filter ensures that the car is receiving clean air, as any particulates could be damaging to the engine. The throttle body allows for more air to pass through the intake as the throttle pedal is pushed. The venturi is there to make sure the car meets FSAE regulation, which mandate the presence of a 20mm air restrictor between the throttle body and the engine. The plenum collects the air and creates positive pressure, allowing efficient flow through the runners to the engine when throttle is opened. The base plate connects the runners to the engine itself, where it is fastened with the screws.
The type of printer you use can have a large impact on the quality of your print. At UGA, we had access to 2 printers, the TAS6 and the Dremel DigiLab 3D45. The TAS6 had a larger workbed for larger prints, used a custom Cura slicing software, had a max printing speed of 200 mm per second, had a layer resolution of 0.05 to 0.4 millimeters, and the nozzle moved in the X and Z axis, while the bed moved in the Y-axis. We found that the bed adhesion was more important in the TAS6 as the snappy movements of the bed caused shifting if not adhered properly. The Dremel DigiLab 3D45 also uses their own specialized slicing software, has a max printing speed of 150 millimeters per second, has a layer resolution of 0.05 to 0.1 millimeters, and the nozzle moved in the X and Y axis while the bed moved in the Z axis. For filament, we had 2 options, PLA and ABS. PLA has a smoother surface finish, higher strength, and requires a lower melting temperature, which usually made printing easier. However, when heated, it was likely to deform. ABS has a higher ductility but less strength, is lighter, and requires a higher melting temperature. This also meant that the bottom was likely to curl during cooling.
The primary design objective of the air intake system was maximizing the volumetric flow rate through the intake. This enables the engine to receive the most air at the outlet of the intake and generate more power. There are many ways to accomplish this, and we've focused in on a few of them. First, minimizing the pressure drop across the intake. This was done primarily by optimizing the convergence and divergence angles of the restrictor near the top of the intake. Next, minimizing turbulence in the plenum, where the air will collect before it's pulled into the engine. This is done by rounding the wall of the plenum and adding a spike in the middle to direct airflow. Lastly, minimize friction. This is done manually after the print is finished, where we polished up the finish by sanding rough surfaces on the interior of the intake. The design process itself consisted of research, where we looked at scholarly papers published online, and we looked at some other teams' designs to draw some inspiration from other FSAE organizations. Then the intake was CAD modeled in SolidWorks. In this, we used multiple configurations to easily test different dimensions. And next, it was tested using SolidWorks flow simulations. The SolidWorks flow simulation is a powerful tool that aided in decision making regarding which design was the best. It allowed us to visualize airflow, as you can see in the picture to the right. It also generates important data on pressure, velocity, temperature, and more, which quantifies the pros and cons of each design.
Printing is an easy step if you know what to look for and how to operate the printer. First, using the TAS6 software called Cura, we can manipulate and slice the model so it's ready for printing. We want to optimize the bed for space, but since we are only printing 3 parts, this is not such a big deal. We also want to account for overhangs so we can reduce the amount of support. We decided to break up our print into 3 different pieces so to limit the amount of support we needed and to also have a full-size part. 3 parts were connected with plastic adhesive and set to cure.
Through the designing and printing process, we ran into some issues and learned some lessons. The printing capabilities and limitations of 3D printers in general, as well as your specific 3D printer, have to be considered in the design process. This means avoiding excessive overhangs, thinking about your printing orientation, and also where you're going to place your supports. The actual dimensions of your print may not be accurate to the model that you designed. This can also be affected by what filament you use, as well as what printer you're printing on. We found that the most issues happen during the beginning layers of the print, and one of the ways we found to remedy this is using the skirt or raft feature. This helped establish a proper flow before printing the actual part.